Have you ever wondered why that perfectly ripe banana on your counter turns into a mushy, brown mess in just a few days? The culprit is an invisible gas, a silent killer of fresh fruit that costs the world billions every year. This gas determines whether your fruit stays fresh or rots away before it ever reaches your plate. Welcome to the Fields of Innovation YouTube channel. Smart farming starts here. Discover the future of agriculture, where we share information about technology applied in agriculture. Today, we're diving deep into the world of ethylene control and uncovering the incredible technologies that are helping us win the fight against food waste. Ethylene is a natural plant hormone that fruits produce as they ripen. It's nature's way of signaling that it's time to mature, soften, and develop flavor. However, once a fruit is harvested, this process doesn't just stop. The ethylene continues to be released, and if it's not controlled, it accelerates the ripening process, leading to rapid softening, decay, and spoilage. Imagine a split screen. On one side, a fresh yellow banana. On the other, the same banana, exposed to concentrated ethylene, turning brown and spotted in a fraction of the time. This is the ethylene problem in action. The scale of this issue is staggering. Post-harvest losses, meaning food wasted after it's been picked, are a massive global challenge. It's estimated that up to 30 to 40% of all fruit losses are directly linked to uncontrolled ethylene buildup. This translates to billions of dollars in economic losses annually and an immense amount of wasted food, water, and energy. This leads us to a critical question. Can we slow down this natural ripening process safely, without resorting to harsh chemicals or sacrificing the delicious flavor and texture we love? The answer is yes, and the solutions are more innovative than you might think. To understand the solution, we must first grasp the science behind the problem. Ethylene, with its simple chemical formula, SHE, is a powerful plant hormone. Despite its simplicity, its effects are profound. In the world of horticulture, fruits are generally categorized into two groups based on their response to ethylene after harvest. Climacteric fruits, such as bananas, apples, mangoes, avocados, and tomatoes, experience a dramatic spike in respiration and ethylene production as they ripen. This means they continue to ripen even after being picked from the plant. On the other hand, non-climacteric fruits like grapes, citrus fruits, and strawberries do not ripen further once they are harvested. They must be picked at peak ripeness. The challenge with climacteric fruits is that they are extremely sensitive to ethylene. Even minuscule concentrations, as low as 0.1 parts per million ppm in the air, can trigger a chain reaction. One ripening fruit can release enough ethylene to accelerate the ripening of all the fruits around it. This phenomenon, known as cross-contamination, is a nightmare for storage and logistics. Visually, you can picture one slightly overripe apple in a large crate, acting as a catalyst that causes the entire batch to spoil prematurely. This is why managing ethylene is absolutely critical for the global cold chain, ensuring that fruit transported across continents arrives fresh and ready to eat. For decades, the industry has relied on several traditional methods to combat the effects of ethylene. The most common and fundamental approach is the use of cooling and ventilation. By lowering the temperature in cold storage rooms, the fruit's metabolic rate, including ethylene production and respiration, is slowed down. Good ventilation helps to circulate air and remove some of the accumulated ethylene gas. While these methods are low cost and widely used, they are often not enough. They can slow the process, but they can't completely stop or remove the ethylene present in the storage atmosphere. To be more proactive, chemical absorbers have been used. The most well-known is potassium permanganate, KMNO. This powerful oxidizing agent is placed in filters or sachets, where it reacts with ethylene and converts it into harmless byproducts. However, these filters have a limited lifespan and must be frequently monitored and replaced, which adds to labor costs and operational complexity. Other systems involve using ozone or ultraviolet UV light to oxidize ethylene in the air. While effective at removing the gas, these methods can sometimes have unintended side effects, such as altering the fruit's natural aroma or causing minor damage to its skin. These traditional solutions, though foundational, often lack the precision and consistency needed for large-scale, high-value fruit exports, paving the way for more advanced innovations. The modern era of ethylene control was revolutionized by a breakthrough in chemistry. The development of 1-methylcyclopropene, more commonly known as 1-MCP. This synthetic compound is a structural analog of ethylene, but with a crucial difference. It binds irreversibly to the ethylene receptors in the fruit cells, effectively blocking them. By occupying these receptors, 1-MCP prevents the fruit from detecting and responding to the presence of ethylene, whether it's produced by the fruit itself or from external sources. It's like putting earmuffs on the fruit so it can no longer hear ethylene's ripening signal. This technology is commercially marketed under brand names like Smart. The application process is highly controlled. Fruits are placed in a sealed, airtight room or container, and a calculated dose of 1-MCP gas is released for a specific duration, typically 12 to 24 hours. Once the treatment is complete, the fruit is essentially immunized against ethylene's effects for an extended period. This method has been a game-changer for the apple, pear, kiwi, and banana industries, allowing them to maintain firmness, crispness, and acidity for months in storage. For example, a Washington apple warehouse can treat its harvest with SmartFresh, enabling them to store the apples and export them around the world with confidence, knowing they will arrive in pristine condition. However, 1-MCP is not a universal solution. Its effectiveness varies depending on the fruit species, ripeness stage at the time of treatment, and storage temperature. While chemical blockers like 1-MCP are highly effective, another frontier of innovation focuses on physically removing ethylene from the air in real time. These are engineering-based solutions that actively clean the atmosphere within storage facilities. One of the most prominent technologies is catalytic conversion. These systems, often called ethylene scrubbers, work much like the catalytic converters in our cars. Air from the storage room is passed over a heated catalyst bed, which contains precious metals like platinum or palladium. The catalyst facilitates a chemical reaction that oxidizes ethylene into harmless carbon dioxide and water vapor. The clean air is then recirculated back into the room. A newer, more advanced approach is plasma-assisted catechesis. This technology uses a low-temperature plasma to generate highly reactive oxygen radicals. These radicals are incredibly effective at breaking down ethylene molecules at ambient temperatures, making the process more energy efficient than traditional high-temperature catalytic converters. Companies like DCL and Breyer are pioneers in deploying these sophisticated systems in large-scale fruit storage, warehouses, and shipping containers. The engineering is complex, requiring careful design of airflow dynamics, humidity control, and regular maintenance schedules to ensure optimal performance. An animation would show air being pulled into these scrubbers, the ethylene molecules being zapped and broken down, and pure, fresh air being returned to protect the fruit. The true power of modern ethylene management comes from integrating these advanced control technologies with the Internet of Things, IoT, and artificial intelligence, AI. This is where we enter the realm of smart storage. In these state-of-the-art facilities, a network of IoT sensors is deployed to continuously monitor key environmental parameters in real time. These sensors track not only ethylene concentrations, but also temperature, humidity, and levels of carbon dioxide and oxygen. All this data is fed into a central control system powered by AI algorithms. The AI analyzes the data and makes intelligent, autonomous decisions. For instance, if ethylene levels start to rise in one section of the warehouse, the system can automatically increase the fan speed in that zone, divert more air to the catalytic scrubbers, or adjust the filtration cycles. This dynamic, responsive approach ensures that the ideal storage atmosphere is maintained with unparalleled precision. The benefits are dramatic. These integrated systems can extend the shelf life of sensitive fruits by an additional 30 to 50% compared to traditional methods. They also optimize energy consumption by running ventilation and filtration systems only when needed, reducing operational costs and environmental impact. For operators, digital dashboards provide a clear, real-time view of conditions, showing ethylene levels dropping and fruit quality being preserved. These technologies are not just theoretical. They are delivering tangible results for farmers and exporters worldwide. In the United States, California citrus growers are using large-scale catalytic scrubbers to preserve the freshness of lemons and oranges, destined for lucrative export markets in Asia, extending their storage life by weeks. In Australia, mango and banana exporters have embraced a combined approach, using 1-MCP treatments at the start of the storage period, followed by continuous IoT monitoring throughout the supply chain to ensure quality is maintained from the farm to the foreign supermarket. Across Europe, cold storage leaders in Spain and France are investing in hybrid plasma catalyst systems to protect high-value stone fruits and berries. The outcomes are consistently impressive. Across these case studies, a common theme emerges: waste reduction of up to 40% and a shelf life extension of 30 to 50%. These numbers aren't just good for business. They represent a significant step forward in our global effort to reduce food loss and build a more resilient food system. Of course, adopting these advanced technologies requires a significant initial investment. The cost of catalytic scrubbers, 1-MCP application facilities, and IoT sensor networks can be substantial. However, for businesses dealing with high-value, perishable fruits like avocados, cherries, or berries, the return on investment can be rapid and substantial. By drastically reducing spoilage rates, exporters can sell a higher percentage of their inventory at premium prices, leading to a significant boost in profitability. Furthermore, the conversation is shifting toward sustainability. Modern ethylene control systems are more energy efficient than older methods, and by preventing food waste, they also reduce the overall carbon footprint of the agricultural supply chain. Wasted food means wasted water, land, and labor. In recognition of these benefits, governments in North America, the UK, and Australia are offering incentives, grants, and tax credits to companies that invest in sustainable post-harvest technologies. An animated chart would clearly show how, over time, the initial cost is dwarfed by the savings from waste reduction and the increase in profits. The message is clear: sustainability and profitability are not mutually exclusive. In modern agriculture, they go hand in hand. Looking ahead, the future of post-harvest ethylene management is incredibly exciting. Researchers are exploring next-generation technologies that promise even greater efficiency and sustainability. This includes the development of nanocatalysts, which can remove ethylene with unprecedented efficiency at even lower energy costs. Another promising area is biodegradable active packaging. Imagine a cardboard box or a plastic wrap infused with natural ethylene-absorbing compounds, protecting the fruit from the inside out during transit. Ultimately, we are moving towards fully autonomous, AI-driven smart warehouses. These facilities will use a vast array of sensors to detect not just ethylene but a whole spectrum of volatile organic compounds that signal the onset of spore. The AI will then orchestrate a symphony of responses adjusting temperature, humidity, and gas composition with surgical precision to create the perfect preservation environment. When integrated with renewable energy sources for cold storage and blockchain for supply chain traceability, we can create a food system that is transparent, efficient, and truly sustainable. Technology and nature don't have to compete. By understanding the natural process of ripening and developing intelligent tools to manage it, we can work in harmony with nature. Together, they can preserve freshness, reduce waste, and ensure that the bounty of our fields reaches tables around the world, feeding more people and building a more sustainable future.